All right, section 8-2 we call special right triangles. And what we're going to do here is we're going to take what we talked about in section 8-1 with the Pythagorean theorem and apply it to just two certain types of right triangles. The first is what we call a 45-45-90 triangle, and the second is a 30-60-90. When we label these triangles, what we're labeling is the angles of those triangles. So the first one we're going to look at, and I said it was a 45-45-90 triangle, is the same thing as an isosceles right triangle. So anytime that you have an isosceles right triangle, since you have one angle that's automatically 90 degrees, since you're looking at a right triangle, then the other two angles have to always be 45 and 45, since we know base angles are congruent. So that's where the name 45-45-90 comes from. Now, looking at this right triangle, since it's isosceles, I've got two side lengths the same. These are my legs, the left and the right. So they've labeled them here with X. And then my hypotenuse is going to be a different length. They label that Y. So using Pythagorean theorem, where I square the legs, add them up and set them equal to the hypotenuse squared, a squared plus b squared equals c squared. In this case, I get x squared plus x squared equals y squared. Well, when simplifying, since x squared and x squared are like terms, I can combine them to get 2x squared equals y squared. And then if I square root everything to get y by itself, I get x times the square root of 2 equal to y. And that's where this first theorem comes from. It says in a 45-45-90 triangle, again, that's how we're going to identify this based on the angle measures, both legs are congruent, so they're equal to each other, whatever that may be, and the length of the hypotenuse is the square root of 2 times the length of the leg. Now, why do we care about this? These two special right triangles we'll look at in this section actually come into play big time when you start looking at trigonometry, whether that be in pre-calc or a trig class later on. When creating what we call the unit circle, we can use special right triangles to explain a lot of how that unit circle is created. So just having a basic understanding now will certainly help you out in the long run when you get into those high-level math classes. Okay. So we're just going to start off here with finding the length of the hypotenuse of two different triangles we have here. So the first thing you want to do, now we've only talked about these 45-45-90 triangles so far, but it's always good to first look at and identify what type of triangle you have. We're going to introduce a second special right triangle here in a little bit, and so we want to make sure that we are clearly identifying which type of triangle we're looking at. In this case, it is a 45-45-90 triangle since I have an isosceles right triangle with my base angles equal to 45 degrees. And knowing that's a 45-45-90 triangle tells me that then my hypotenuse has to be equal to the square root of 2 times the leg. And as a reminder, our hypotenuse is always our longest side, always across from the right angle, and the other two sides then are always labeled my legs. When we're talking about both right triangles and isosceles triangles, we name the remaining two sides legs. So in this case, once you know what type of triangle you have and you know the rule you're going to apply, go ahead and use substitution. Well, my hypotenuse is just h, I don't know that yet, that's still my variable, is equal to the square root of 2 times the length of my leg. My leg here is labeled with 9. And the last step I'm going to do here, anytime that you're leaving something in radical form or you leave a square root in your answer, if you're multiplying that radical or square root by an integer, you want to write the integer first. Not that it's wrong to say square root of 2 times 9 as opposed to 9 times the square root of 2 or 9 root 2. It's just good form to write that integer first, and it helps in that you're not going to potentially mess up putting that 9 under the radical. You don't have to write the multiplication in there then. That's an implied multiplication with the 9 in front, and it's just good math form. So that's how you're going to see your answer left in these problems. All right, part B. Again, I always just like to first identify what sort of triangle I'm looking at. Again, isosceles right with two 45-degree angles. So this is a 45-45-90 triangle. We just have one thing to remember for 45-45-90 triangles, and that's that the hypotenuse is equal to the square root of 2 times the leg. I haven't even looked at what I'm given here. I'm just going to always start with writing down those things when I'm looking at a 45-45-90 triangle, because I should be able to then solve with just substitution. Looking at my triangle, again, hypotenuse is always across from the right angle, so my hypotenuse is my variable x, and my legs are the other two sides. So I'm going to substitute hypotenuse for x. Square root of 2 times the length of my leg is 2 root 2. Okay. Now this, hopefully you're looking at that and you're saying, hey, I should never have two radicals being multiplied by each other because that can be simplified. So I'm going to keep working on some simplification here. And I'm going to start by just rearranging my terms here, and I'm going to write 2 out front. Again, like we said, we like to start with that integer, times the square root of 2 times the square root of 2. So now let's talk about this. What is the square root of 2 times the square root of 2? Anytime you're taking the square root of a number times the square root of that same number, you're just going to get that value out. So square root of 2 times 2 is really just 2. And then don't forget about the 2 that we already had out front. So x is equal to 2 times 2. So our last simplification, we're just going to do that multiplication. And our x value is 4. So my leg had a length of 2 root 2. My hypotenuse then had a length of 4. Let's look at one more. What is the length of the hypotenuse of a 45, 45, 90 triangle with a leg length of 5 square root of 3? So this time, I'm not going to write down that I have a 45, 45, 90 since it's written out for me right here, but I'm going to write down what I know about 45, 45, 90 triangles, and that's that the hypotenuse is equal to the square root of 2 times the leg. And again, I'm going to go ahead and just start with some substitution. I don't know the hypotenuse, so I'm going to leave that my variable h. Square root of 2 times my leg is equal to 5 times the square root of 3. So again, your answer will never be completely simplified if you have two radicals being multiplied by each other, because we can simplify multiplying radicals. And again, I'm just going to start by rearranging my terms, leaving the integer out front. Square root of 2 times the square root of 3. Now, hopefully you remember probably from an algebra class about some properties of radicals. Meaning, when I'm multiplying two radicals together, I can actually multiply the value underneath those radicals and combine them. So in one last step, I can combine square root of 2 times square root of 3 to actually be the square root of 6. 2 times 3 is 6. We can multiply radicals. And then don't forget about that 5 out front. So my final answer is that my hypotenuse has a length of 5 root 6. Okay? So that's applying that method of 45, 45, 90 when I know the leg and I'm looking for the hypotenuse. All we really did there was substitution and then a little bit of simplification with radicals. That might be some review for you. Maybe you haven't seen that in a while, but pretty straightforward. Plug and chuck. Well, let's see what happens when I'm given my hypotenuse and I need to work backwards to find my leg. So I've got a multiple choice problem here and a picture. Notice I've got isosceles right triangle. Got those two 45-degree angles. So right off the bat, I'm going to do the same thing I've done so far every time. 45, 45, 90, which tells me that my hypotenuse is equal to the square root of 2 times the leg. And again, if you want to go ahead and label your picture, you definitely can. Hypotenuse is this length of 6 since it's across from the right angle. It's our longest side. And then in this case, we don't know either of our legs, and they've been identified with the variable x. So, again, we're just going to use substitution, replacing what we know. My hypotenuse has a length of 6, and I don't know my leg. That's going to be my value x. So, still the same type of process we did in the previous examples. Only difference here is now instead of solving for my hypotenuse, or by just simplifying the right-hand side, we're going to have to do one step of algebra, and that's going to be to get this x by itself. So I'm multiplying it by the square root of 2. So to undo multiply, we're going to divide both sides by the square root of 2. So now I have x is equal to 6 over the square root of 2. Now, again, I'm hoping that this next step is review for you from algebra. If you've never seen this before and you have questions, please let me know and I'd be happy to go over it. But one thing that we work with when we're working with radicals is that we never want to have a radical in our denominator. It kind of dates back to that concept we talked about in class a couple weeks ago with back in the day when it was hard to identify what square roots were. We didn't have a method for it before calculators could do it for us. It was an easier way to estimate those radicals as if we only ever had them in the numerator. And so this next process is what we call rationalizing the denominator. And that just means anytime that there's a square root in the bottom of your fraction, you need to get rid of that. And to get rid of that, what we're going to do is we're going to take both the top and the bottom of my fraction and multiply by that square root value. So in this case, I'm multiplying both the numerator and the denominator by the square root of 2, and then simplify. On top, 6 times the square root of 2 is just 6 times the square root of 2, over square root of 2 times square root of 2, if you remember from that second example we did, is the value 2. Anytime you're multiplying two radicals by themselves, it's equal to that value. So now I've got x equal to 6 square root of 2 over 2, but then look at your integer values. If you can simplify, keep simplifying. Since 6 over 2 can be reduced to, if I divide both by 2, I can get 3 left on the numerator and my denominator goes away. My final answer is going to be 3 square root of 2 is equal to x. And you can see that that's option B up here. Again, that's the process of rationalizing the denominator. We do not want to have radicals in the bottom of our fractions anytime, not just with special right triangles, but anytime that you're going to give an answer. So you'll want to make sure in your homework that you're doing that rationalizing the denominator process to make sure that you get the full credit for those problems. All right, let's try one more. The length of the hypotenuse of a 45, 45, 90 triangle is 10. What is the length of one leg? So I'm told it's a 45, 45, 90, so I'm going to, again, the same thing I've done each time, start with this formula that says that my hypotenuse is equal to the square root of 2 times the leg, and then I'm just going to do some substitution. My hypotenuse in this case is equal to 10. I don't know the leg, I'm going to use variable x. Hopefully this is looking familiar from that last example. Divide each by the square root of 2 to get x by itself. I'm going to go ahead and come up here. X is equal to 10 over the square root of 2. We don't want to leave the square root in our denominator, so we need to rationalize that denominator by multiplying both top and bottom by the square root of 2. My numerator becomes 10 root 2 over square root of 2 times square root of 2 is 2. And that last step is to simplify those integer values if you can. 10 divided by 2 is 5 square root of 2. So my missing leg in this case is 5 root 2. All right, one last example looking at a 45, 45, 90 triangle, putting it into a little bit of context here. It says a high school softball diamond is a square. The distance from base to base is 60 feet. To the nearest foot, how far does a catcher throw the ball from the home plate to second base? So, home plate to second base, if my home plate is here and my second base is here, it's this distance here marked with a dotted line and the lowercase d. Now, knowing that this is a square tells us that this side is congruent to this side, so this is also 60 feet, and this has to be a right angle, so these two angles have to be congruent and 45 degrees. So in this case, I wasn't given, I wasn't specifically told via picture or text that I had a 45, 45, 90 triangle, but I can identify it based on what I know from the given information. So now if I look at just this right-hand side, the dotted line being my hypotenuse, I've created a 45, 45, 90 triangle. And I know that in a 45, 45, 90 triangle, my hypotenuse is equal to the square root of 2 times the leg. Now replace what we know. I don't know the hypotenuse, that's my variable d, times the square root, or square root equals square root of 2 times my leg is 60 feet. Now, always pay attention to what you're asked for. In this case, I'm asked for the distance to the nearest foot. So I don't want to leave my answer as 60 root 2 like we had in the previous problems. I want to actually figure out to the nearest foot what is 60 times the square root of 2. So grab your calculator. I'm going to start with the square root of 2. Using this calculator, you put the 2 first, then click the square root button, and multiply by 60. To the nearest foot, I'm going to round this up to 85 feet. So that distance from home plate to second base is about 85 feet. So always make sure that you're paying attention to how they want you to leave your answer and do so accordingly. Okay, That's why we're going to talk about 45, 45, 90 triangles. We have one other special type of right triangle that we like to talk about, and that's what we call the 30, 60, 90 triangle, which hopefully you guessed means that the angles in that triangle are 30 degrees, 60 degrees, and 90 degrees. Now, unlike the previous special right triangle, I don't have congruent legs in this case. In a 30, 60, 90 triangle, I classified my sides using these three terms. I still have the hypotenuse, which is always across in the right angle. That's the side here. And then I have what's called the short leg and the long leg. The short leg will always be across from the 30-degree angle. The long leg will always be across from the 60-degree angle. You can remember that from chapter 6 when we classified lengths of sides based on angle measures. Also, most of the time you'll be given a picture, which typically it should be very clear which is your short leg and your long leg. So when we're looking at 30, 60, 90 triangles, we have two formulas to remember. The first tells us that in a 30, 60, 90 triangle, our hypotenuse is 2 times the short leg. And our second one says that our long leg is equal to the square root of 3 times our short leg. So all we'll need to know is those two formulas when we're looking at 30, 60, 90, but we will have to do a little bit of work to figure out which formula we're going to be using, or we may be using both to get our final result. So let's go ahead and put those into action here. We're given a 30, 60, 90 triangle here. And before we even look at what we're looking to find, let's label our sides. Across from my right angle is going to be my hypotenuse, just like it always will be. Then my short side is this side over here marked D, or my short leg. And my long leg is then going to be the remaining side, the length of 5. So hopefully that's clear to you. If you're not sure how to label a triangle, always ask. So I'm asked to find the value of D in this case, and it says leave it in simplest radical form. So I've got a 30, 60, 90 triangle. Again, I'm going to label that. And I'm looking for the short leg. But if I look here, my two formulas both involve the short leg. So I need to look past just needing the short leg and look at what I know. I'm given the length of my long leg. So I'm going to choose this second formula here. Long leg equals the square root of 3 times the short leg. That first formula wouldn't have done me much good because I don't know the length of the hypotenuse at this time. So I couldn't have just doubled that. So I'm going to need to use a second formula. And once you know which formula you're using or what you're looking at, the rest is just substitution like with our previous examples. So I'm going to replace long leg with 5, since my long leg has a length of 5, is equal to the square root of 3 times my short leg is the variable D. And now, this should look like we did in the past couple examples. I need to solve for D by dividing both sides by the square root of 3. So I get a value of D is equal to 5 over root 3. Now remember, that's not going to be considered simplest radical form. Simplest radical form, we need to always rationalize the denominator. So now I have D is equal to 5 times the square root of 3 as my numerator, all over 3. Note in this case, unlike the previous two times we've rationalized the denominator, 5 over 3 doesn't reduce. So this is my final answer. My final answer is still a fraction. My short leg has a length of 5 root 3 over 3. So even though it doesn't look like it's a nice number, that's okay. A lot of these will have those square roots still left in the answer, and that's okay. Now the second part asks us to find F and to leave it in simplest radical form. Well, F in this case is my hypotenuse. If I go back up to these two formulas I know, I only have one that involves the hypotenuse, and I need to know the short leg to find the hypotenuse. Well, I did just find the short leg, so I'm going to be able to use that formula to solve. And that formula says the hypotenuse is equal to 2 times the short leg. So replacing what we know, the hypotenuse is the variable f. So f equals 2 times my short leg. We just found that was length d, 5 square root of 3 all over 3. And so the last thing you want to do is multiply your 2 times this fraction. If you want to, you can put 2 over 1. And when we multiply fractions, we just multiply across the top and across the bottom. So f is equal to 2 times 5 gives me 10, square root of 3 all over 3. And that's going to be my final answer for the hypotenuse. So you'll certainly have instances where your answer doesn't look like it's a nice answer. There are not going to be a lot of just integer answers. There's going to be a lot of radicals another name for square root, in your final form of the answer, and that's okay. A lot of fractions as well, and that's okay. If you need help with simplifying those, always just shoot me an email, and I'd be happy to go over that with you. All right, just a few more examples here. It says an artisan makes makes pendants in the shape of equilateral triangles. The height of each pendant is 18 millimeters. What is the length S of each side of the pendant to the nearest tenth of a millimeter? So I've got my pendant here, and now other than the title up here, applying the 30, 60, 90, I'm not really shown anything on that picture about this triangle. But I am told that it's an equilateral triangle, meaning all of the angles are congruent. And we learned that anytime we're talking about an equilateral triangle, all of my angles have to be 60 degrees each, since they're all the same and they add up to 180. So I know that this here is a 60-degree angle. Now, they've left us the height here. So if I draw on the height, and I look at just either the right or the left, I'm going to look at the right, for example, the right side of this triangle, I've now created a right triangle. And if this whole angle at the top is 60, by drawing in that altitude, I've also made a median, or cut that angle in half, and this is 30 degrees. And I'm just going to go ahead and sketch that over here a little bit bigger, a little bit clearer to see, so that we're all kind of looking at the same thing here. You know, I'm going to try that again. Okay, so I just did the right side, got this right angle here, this is my 60-degree angle, this is my 30, and I know one thing in here. I know the length of this left-hand side is 18. That would be like the height of that whole pendant, and in this case, let's go ahead and label our sides. 18 is our long leg. We have our short leg over here and across from the 30 degree, and then across that 90 degree is our hypotenuse. So I haven't even looked at what I'm looking for here yet. I just took that equilateral triangle, split it in half, made a 30, 60, 90 triangle. So what am I asked to find? I'm asked to find the side length of the pendant, which is like the hypotenuse here, so I'm going to label that S. Now, in order to find the hypotenuse, like we said in the previous example, I only have one formula that uses hypotenuse, and that is the hypotenuse is equal to 2 times the shorter leg. But I don't know the short leg in this pendant problem. I'm not given that, so I can't go right ahead and plug in that formula using hypotenuse. I need to first use the formula using the longer leg to find the short leg, then I can go ahead and use the hypotenuse formula. So the first thing I'm going to do is find the length of my short leg by using long leg equals the square root of 3 times the short leg. Okay. And I'm going to substitute in what I know. I know that my long leg has a length of 18. So 18 is equal to the square root of 3 times the short leg. Oh, and you know, I'm going to go ahead and put a variable in there instead of writing out short leg. We're going to call the short leg x. And solve for x by dividing both sides by the square root of 3. So my short leg is equal to 18 over root 3. And just like we have before, we want to rationalize that denominator, which gives us 18 times the square root of 3 all over 3. And if you can, reduce your integers. 18 divided by 3 is 6, so my final answer is 6 root 3. So my short leg has a length of 6 times the square root of 3. Now I can go back and pull that hypotenuse formula that says in a 30, 60, 90 triangle, my hypotenuse is equal to 2 times the short leg, since I know the length of my short leg. So my hypotenuse, that's what we said is the variable s, is equal to 2 times the short leg. We just found that to be 6 times the square root of 3. And again, pay attention to what your question is asking. In this case, we don't want it left in simplest radical form. We want it left to the nearest tenth of a millimeter, meaning round to 1 decimal place. So you can plug that whole thing right there, right into your calculator. 2 times 6 times the square root of 3. And enter. To the nearest tenth of a millimeter, I get 20.8 millimeters. So each side length of this pendant is about 20.8 millimeters. So if you're not given the short leg, you may have to use both formulas to get your final answer. The short leg is used in both, and you can, if you're given one of the side lengths, you can always work to find the other two. Just make sure that you are using the right formula at the right time. A lot of just plug and chug once you figure out where to go from there. So these last two I want you to try on your own. You're looking at two different examples here, and you're looking for X in each. So go ahead and give those a shot, and then I will reveal the answers. So for part A, you should have got X is equal to 3, and I've left my work here for you to look at. In part B, you should have got X is equal to 6 times the square root of 3. And again, my work is there for you to look at it. If you have questions, please don't hesitate to ask.